Everybody, it's Professor Mitchell. We are finally finishing up Chapter 10 today. We're going to look at 10.7, which is all about complex numbers. In this section, we will write square roots of negative numbers in the form b times I, add or subtract complex numbers, multiply complex numbers, divide complex numbers, and we'll end by talking about how to raise I to powers. And this goes under SLOB, along with most of the rest of this chapter. All right, so complex numbers. When you look at certain equations like x squared plus 1 equals 0, those equations don't have any real solutions. So let me switch over to the tablet just to convince you of that. All right, so here's the equation x squared plus 1 equals 0. So one way I could try to solve this equation is by subtracting 1 from both sides. And that would give me x squared equals -1. Now, if that number -1 was some positive number, especially a nice positive number like 4 or 9 or 16, then x would just be the square root of that number, right? Like if x squared was 9, say, then x, well, one possible solution for x at least is the square root of 9. In the very next section, section 11.1, we're going to talk about what is the correct way to do this. And I'm actually going to give you a preview of that right now. X could actually be the positive or negative square root of 9. Which would make x positive or -3. So if I tried to do that, and let's forget about the plus or minus for a second. Let's say we're just looking for one solution. Well, one solution would be the square root of -1, if there was such a thing. But inside the world of real numbers, there is no such thing. So about, I want to say 400 or 500 years ago, somebody realized that if we expanded real numbers into a bigger set where we did allow for equations like this to have solutions, that it would open up a lot more things that we could do. All right. So let me tell you about that. I'm going to switch back to the presentation. Okay, so in what's called the complex number system, this equation, x squared plus 1 equals 0, has solutions. And the complex number system is based on what's called the imaginary unit, which is written I. All right, and this is a funny little cartoon that I came across at some point. So I is telling the number pi to be rational because, of course, pi is an irrational number. And pi is telling I to get real because I is not a real number. All right, so the imaginary unit, which is written I, is the number whose square is -1. That is, I squared equals -1, and I is the square root of -1. So to write the square root of a negative number in terms of I, use the property that if A is a positive number, then the square root of -A is equal to the square root of -1 times A, which comes out to I times the square root of A. So for the first batch of examples, I've got quite a few of them here. We're going to simplify and then write in terms of I, which basically means the same thing. And we'll end this batch by multiplying and dividing. All right, so going back to the tablet. Gizmo squawking in the background. Okay, so the square root of -49, to use that property that I was just talking about, and you know, once you get used to this, you're not going to have to write this many steps. Start off by writing this as -1 times 49. And then I actually, just this once, I'm going to put a little extra step in here. This is the square root of -1 times the square root of 49. The square root of -1 is what we're calling I. And the square root of 49 is 7. So the way you're going to write this answer is 7I. All right. And by the way, before I forget, I'm really not a big fan of the term imaginary unit. It makes it sound like fairy tale stuff. There are certain professions that actually use complex numbers in their work. And so to those people, these numbers are not imaginary. All right. One example is electrical engineering. In electrical engineering, they use complex numbers. Okay, next example. I'm going to start this one the same way by writing -3 as -1 times 3. Oh, I know I said just this once. I'm going to do it one more time. Okay, now the difference between this problem and the last one is that the square root of 3 doesn't simplify to anything nice. So this one you would just write as I times the square root of 3. Okay. Now, there may come a time when you start wondering, okay, Mitchell, why are you writing it like that and not like this? Well, I guess that's technically correct. The reason that we traditionally like this better is because there can't be any confusion about whether the I does or doesn't go under the radical. All right, you can see writing it this way, there could be a little bit of confusion, especially if, I don't know, it was sort of ambiguous whether that I was under there or not. So if you put the I in front of the radical, then you don't have to worry about it. Everybody will read it the same way. All right, next, write in terms of I, which basically means the same thing as simplify. So what these problems have in common is that the numbers there, I'm talking about the 32 and the 20, they are not perfect squares, but they do have factors that are perfect squares. So here's what I'm going to do. I'm going to, first of all, separate the -1. And then I'm going to break off the biggest perfect square factor of 32 that I can. So this part is basically just simplifying the square root of 32, which you already know how to do. So I'm going to write that 32 as 16 times 2. And now the square root of -1 is I. The square root of 16 is 4. And the square root of 2 is just the square root of 2. So I would write this answer as 4I times the square root of 2. Make sense? All right, letter B would be a good one for you to try. If you're feeling frisky, pause the video, try it, come back and compare notes. All right, so that 4, we'll just leave that there. And I'll put a -1, and then the biggest perfect square factor of 20 is 4, and then the leftover is 5. Okay, so square root of -1 is I, the square root of 4 is 2, and the square root of 5 is just the square root of 5. So putting it all together, you get that 4 times the square root of 20 simplifies to 8I times the square root of 5. All right, and finally, one multiplication, one division. So this is one of those times that I really miss having a face-to-face class. I always like to have a fun discussion about what is the right and the wrong way to do this problem. Okay, so I think what I'm going to do this time is I'm going to show you the right way. And then I will just very briefly mention the wrong way. My students have always been very good at sort of pegging the wrong way as the wrong way, which has always impressed me. So the right way to do this is to write the square root of -4 as 2I, and then write the square root of -9 as 3I. All right, and now if we multiply those together, 2 times 3 is 6. I times I is I squared. Do you remember what we said earlier about I squared? We said it pretty fast. We said that I squared was -1. All right, so the square root of -4 times the square root of -9 would come out to -6. It comes out to a real number. Okay, so that's the right way to do it. Unfortunately, what doesn't work, and let me make this very clear that this is the wrong way, so don't do it this way. Square root of -4 times the square root of -9. You might think that you could use the product rule on that. And that would actually give you a different answer, wouldn't it? -4 times -9 is +36. The square root of 36 is 6, which is not the same answer we got doing it this other way. The reason this doesn't work, and it doesn't, is because, so I was trying to use the product rule for radicals there, the thing that says the square root of a times the square root of b is equal to the square root of a times b. Well, if you go back to that section and you read the fine print, there was a note on that product rule that said that this is only if a and b are real numbers. So that does not apply in this problem. Okay, so that's why we have to do it the way we did it. All right, letter B, believe it or not, actually ends up being a little simpler because what you can do is just write this as the square root of -1 times 40, square root of -1 times 8. So you're going to get I times the square root of 40 over I times the square root of 8. And then you can just cancel out those i's. So this ends up being the same thing as the square root of 40 over the square root of 8, which by the quotient rule for radicals, which does apply because the square root of 40 and the square root of 8 are real numbers, just comes out to the square root of 5. All right, so like I said, that one ends up being a little simpler. All right, so what exactly are complex numbers? A complex number is a number that can be written in the form a plus b times I, where a and b are real numbers. Notice, first of all, that all real numbers are automatically complex, all right, which tends to create a little bit of confusion. It's sort of like saying that all squares are rectangles, which is true. But when you picture a rectangle, you usually picture a rectangle that's not a square, all right? And the reason that real numbers are complex is because you can just set b equal to 0 in this a plus b times I. So if b is 0, you get a plus 0 times I, which is just a, okay? A complex number is called a pure imaginary number if a is 0 and b is not 0. So I think almost all of the numbers in the first batch of problems, actually up until we got to the multiplier divide, those were all purely imaginary, right? 7i, I times the square root of 3, 8i times the square root of 5. Those were all pure imaginary numbers. All right, adding and subtracting complex numbers, it turns out, is very, very easy because all it is just combining like terms. So I just have a couple of problems here. And of course, I've got these all ready to go on the tablet. So let's go over there. And here we go. So first we have 5 minus 3i plus 7 minus 8i. Nothing tricky about this at all because it's addition. I really don't need the parentheses. So you can just put the real parts together. The real parts are the 5 and the 7. And then you can put the imaginary parts together. That's the negative 3i and the minus 8i. Okay, I really don't have to group them like that. I'm doing it hoping that it might make it a little more clear what I'm doing. 5 plus 7 is 12. Negative 3i minus 8i is just negative 11i. All right, so the sum of these two complex numbers is 12 minus 11i. Very, very easy. Subtracting is almost as easy. You just have to be careful, and I know you've seen this before, about the minus sign outside the parentheses. So you might want to think of this as adding the opposite, like I'm always telling my pre-algebra students. Change this to addition of the opposite. To make an opposite complex number, you change all the signs. And that would give you 2 plus negative 2. And then plus negative 4i. Negative 4i plus I. Negative 2 plus 2 is 0. Negative 4i plus I is minus 3i. Now, be very careful with your online homework. Sometimes they actually want you to write the answer like that, which I am not a fan of that because I think it looks nicer like this. Okay. But there is at least one textbook that I use where they actually want you to put the 0 minus 3i, and they will actually mark it wrong if you just put negative 3i. I don't agree with that. Unfortunately, I don't make the rules with the online homework. Okay. So just read the directions. All right. Next, we have multiplying complex numbers. So remember that I squared is negative 1. That's key for any multiplication problem. And we will look at these examples. All right, so first we have negative 2i times negative 11i. That's actually pretty simple, similar and simple, but it's similar to the square root of negative 4 times the square root of negative 9. Just multiply negative 2 times negative 11 is positive 22. I times I is I squared. And what's I squared again? It's negative 1, right? All right, so the product of those two numbers comes out to negative 22. Next, we have the square of 6 minus 3i. Remember to FOIL this, or use your special pattern for squaring a binomial. Either one of those will work. I think most people tend to like FOIL, so I'll go with FOIL. 6 times 6 is 36. 6 times negative 3i is minus 18i. Negative 3i times 6 is another minus 18i. And then negative 3i times negative 3i is plus 9i squared. Okay. Combining the like terms in the middle. Well, let's start with the 36 and then minus 18i times, or not times, minus 18i minus 18i is minus 36i. And then because the square, because I squared is negative 1, that means that 9i squared is minus 9. So this comes out to 27 minus 36i. All right, and finally we have 1 minus 2i times 1 plus 2i. You could also FOIL that one, but I would prefer to do it this way. Notice this is an a minus b times an a plus b. And whenever you multiply an a minus b times an a plus b, you get an a squared minus b squared. Playing the role of a is 1. Playing the role of b is 2i. So that gives you 1 minus 4i squared. And once again, I squared is -1, so that gives you 1 minus 4 times -1, which is 1 plus 4, which comes out to 5. So another one that gives you a real number answer.